Hello team, and welcome to another video guide, this one for programming assignment 3, the parser. In this video, we'll be using the Python language and the PLY library. One of the first things we will do is deserialize, read in, input, the programming assignment 2 CLX file, the thing you produced at the end of programming assignment 2. We'll then talk about how to use those programming assignment 2 tokens as a lexer and feed them in to our newly created parser. In order to have our parser do something useful, we'll need to know how we want to represent our abstract syntax tree, the ultimate output of parsing. And then we'll spend quite a bit of time defining our parser by writing down context-free grammar rules. This is the fun part. And we'll pay attention to line numbers and error handling. Once we've done all the parsing, we'll have to serialize the abstract syntax tree, print it out in the format the grading server is expecting, and then we will do a bit of a live submission demo. Those are always fun and never run into any problems. So let's get started. I'm assuming that you've had a chance to read the Programming Assignment 3 description, web page in advance. We'll refer to it a few times. I've already downloaded and extracted PLY, and one of the first rules is that we have to name our file main.py. So we'll just get started with a little comment. This is a parser for PA3 for cool. All right. And just to reiterate, one of the first things we will need to do is read in the CLX file. We will need to sort of deserialize that file into tokens. We will need to feed those tokens into the PLY lexer format. We will want to define our AST representation, or at least think about what that's going to be. We will need to define our PA3 parser as grammar rules, and then we'll need to serialize our AST, print it out. So the first thing to do is to read in this CLX file, which is specified on the command line. And we'll use some system functions in order to do that. Our tokens file name is just the first command line argument. Our tokens file handle, well, we're just going to call open on the tokens file name. We're going to open it for reading. We use the same trick as before to get all of the tokens lines. We'll just take our tokens file handle and read all the lines, and then we'll be very nice and close our tokens file handle. And because this deserialization is tricky, if you haven't done it before, we're going to test early and often. So I'm going to want to print out all the tokens lines. All right, well, where do we get sort of a reasonable input? We want to be parsing cool files. Something like this, a very simple cool program with one class and one attribute. Actually, in cool, that's written like this, x:\int, right? This is what we'll want to be reading in. But someone has already done the lexer for us. Someone, you. So we will actually use something like the reference lexer, right, and produce a list of these tokens. This is what we will actually be reading in. Right, and I'll just copy those to remind ourselves, right? So the input here looks a bit like that, and we'll just move all of that over and make all of that a comment. So this is the sort of thing we'll be reading in, right? But what I want is more like, well, the first one is a class on line 1, and the second one is a type on line 1 that's main, and the third one is an lbrace on line 1, that sort of thing. I don't want them to be spread across 2 lines here and 3 lines there and 2 lines there. I want each token as its own little tuple or its own little entry. That's the deserializing part. We're going to interpret this particular file format. And we're going to be reading these things one line at a time. So let's see how that goes. Again, the first thing we want to do is just test it. Let's see if we've made any mistakes so far. If I run python main.py on our test CLX file, we see all of the output we were expecting. Oh, but notice we've got this carriage return line feed stuff. We'll want to strip that out. So I'll make a little helper function to get the next token line, and I'll remember to strip out all of that white space. Our helper function is going to refer to the tokens lines variable. Sometimes it's nice to tell Python you're referring to a global variable like that, so it reads from the right place. And the result we want to return is the 0th position in that list. Oh, wait, let's, while we're here, let's strip off that white space at the end. And then we use this trick in Python to drop the 0th element and retain all of the rest. And then we can return the result. So we have an approach that can print out a number of token lines. And let's actually test that a few times. We'll just try to print out the first 3 lines and see how well that works. 1 class 1. All right, that looks pretty good. But now I want to convert them into these tuples, the actual tokens that we're going to be reading in. And just for simplicity, so everything is a triple, if there isn't a lexeme specified, we'll just recopy, for the class token, the word they typed in was class. Right, so we'll just reuse the token type as the lexeme. So I'm going to come up with a list of PA2 tokens. It's initially empty. This is the list I want, right? It's like each one of these in a list. And I'm going to get it by reading the lines from the input one at a time. So while we haven't read all of the input, well, we know from this particular format that the first thing we read is always the line number. And we'll use our helper function to get that. And then the next thing we read is the token type. And then for the token lexeme, most of the time we can just reuse the token type to get that. But for certain tokens, like if the token type is one of, identifier or maybe integer or type, this may not be a complete list, then actually we get the real token lexeme by reading in the 3rd line. Like up here, right, main, this is the lexeme associated with the type. All right, so now we have those 3 parts. So I can just say, oh, well, PA2 tokens, I will add on to this list. It's whatever we had before plus this new tuple of the line number, the token type, and the token lexeme. And if this works, let's print out the PA2 tokens and see if it works. All right, so we'll do a little more testing. All right, can we run through this? Well, now we see we have one token that's 1 class 1, another one that's 1 type main, brace on line 1, an identifier that's X, a colon on line 2. So we have successfully deserialized the input. Interestingly enough, just for convenience, whenever we have both sort of lexing and parsing at the same time, by convention for PLY, tokens are uppercase. So I'm actually going to convert the token type here to uppercase just to make it easier to read, to make it look a bit more like their documentation. Let's try this again. So now we have class, colon, semi. These are big terminals, right? Tokens that we can take a look at later. All right. Well, this is seeming pretty good. And now we're reaching the point where we have to integrate with PLY. Essentially, we want to write a parser, but instead of having it call somebody else's lexer, whenever it wants to get the next token, it's just going to peel something off my PA2 tokens list. That's going to be pretty good. So how do we integrate with one of these PLY lexers? Well, I'm going to spend some amount of time reading the PLY documentation. How did I get here? Just from the PLY webpage, which is linked. And we take a look at the documentation, and not Lex, but Yak, our parser. And it turns out down around near miscellaneous Yak notes, they notice by default they rely on their own internal lexer for tokenizing. However, you can supply any alternate tokenizer you want, like the PA2 tokens, that's what we want. But you have to have some sort of lexer object that has a token method. All right. I can do that. So I need a lexer object. So this is going to be, we want to use the PA2 tokens as our lexer. All right. And they say we have to have a token method, and maybe this takes some sort of argument. All right. Now, what we're going to do is every time they ask us for another token, we will just peel one off the PA2 tokens list. One possibility is that we are actually already at the end of the file. We could have read over all the tokens and there could be none left. at which point we'll just return none. But otherwise, we can peel something off the tokens list. We have the line number, the token type, and the lexeme, and those are the first PA2 token available. And we will peel that off, we'll remove it. It's one of these 1: maneuvers. And now we need to somehow communicate this to Python Lex Yak in the format it expects. And you may actually remember, if you did programming assignment 2 in Python, the way they internally represent tokens in Python is with this Lex token constructor. All right? And they indicate that the token has a token type and a token value and a token lexpos. Right here they are calling token to get it. So I will just make a little commented note of that. Those are the fields that we're going to have to fill out. So my token, well, it's going to be one of these Lex token things from them. And then I will set the token type to be equal to our token type, the one we got from PA2. And I will set the token value, that's their word for the lexeme, which I also can't spell, which we also got from PA2. And the line number, well, that was just line, which we got from PA2. And the lexical position, that's actually for counting characters, which many real-world parsers and lexers do, but we do not make you do for these assignments. So we will just leave that at 0 for now, and we can return the token. All right, so we've created a token that integrates with them. And our PA2 lexer, since this is a class, we will need to instantiate it. Right. We have one of these objects. Now, notice we're referring to this Lex token type, and I haven't defined it yet. So we're going to need to bring in some of these files from PLY. And indeed, we're going to need lex.py again, but this time we will also need yak.py. So I'll just copy both of those into the current directory so that we have them. And up here at the top where we were importing sys, from Lex, I need to import this Lex token definition. How do I know it's there? Here it is right there. Notice that obnoxiously, they don't actually have an initializer. They just have a printout. That's why I had to assign to all of the fields manually. What kind of software engineering is this? Anyway, this is the Lex token class. And while we're here, we'll also want to import their parser. All right, so now to figure out how to use their parser, this is where we'd start looking for fun examples in their documentation. All right. They have a Yak example of expression gets expression plus term, expression gets expression minus term. Oh, that looks pretty good. Let's see if there are bigger examples as time goes by. Start is foo, reading through all of these tables. Ideally, we've read through this documentation in advance. Oh, precedence and associativity. Well, that sounds like it would be really helpful. Debugging output, we may use this later if there are shift-reduce conflicts. Oh my gosh, so much debugging output. Panic mode error recovery, we may not need. When do syntax errors get reported? Oh, line numbers and position tracking. Oh, we'll definitely need that. That's good stuff to know about. Abstract syntax tree construction? Oh, we'll definitely need that too. Man, this documentation is amazing. Wow, so nice. But it's not necessarily telling multiple parts. Oh my gosh, that's like one too many for me. But it turns out, and this is fun, that PLY actually comes with a bunch of built-in examples. Like in their calculator directory, right, they list all of these things that we looked over before. Like, oh, it looks like you need to list all of your tokens first. Well, we will go back here, and now it is time to define our PA3 parser. And one of the first things that we're going to do is define all of the possible tokens. It won't necessarily know what they are unless we say what they are. And you notice that they're doing them in uppercase by default. Well, so are we. We changed all of our token type names to be uppercase up here to match with that easy convention. So we don't have name and number, but we will have things like plus and times and integer and class and identifier and type and colon and semicolon, and I'm sure there are more, right? more here. Where would you get this list? From the PA2 webpage. So we will need to list all of our tokens. And now it's time to actually just start writing out these rules. So let's go back to their simple example. And this is how they write down a particular rule. And we'll just copy it over here for just a moment so that we can see how it goes. We would be tempted to write something like in class, expression goes to expression plus expression. And I will leave all the tokens or terminals in uppercase, or expression minus expression, or integer. This is the sort of grammar rule we'd write in class. Well, the way you do it in PLY is you take each one of these rules individually and you write it out as a little Python method, right, that starts with a P for parse. So here's their way of parsing an expression based on plus. Expression goes to expression plus, we don't have terms. We just have expressions. And we could have another one of these that would be expression goes to expression minus expression. So for each one of our grammar rules, we are going to end up with a little very small Python method. And we'll talk about what to put here later, this P0, P1, P3 part. I'll explain how that goes, but before we talk about writing down these rules, we need to decide on how to represent, pardon me for just a moment, our abstract syntax tree. Conveniently, they have documentation on it that I totally can't find, AST construction. And they mention that there are two ways to do this. A minimal way to construct a tree is simply to create and populate a tuple or list in each grammar rule function. Another approach is to create some classes, bin, op, number. In this Python video, I'm going to use the simple approach, and you can check out the OCaml video if you want to see something that's a bit more well-typed. So getting back to this, we will essentially choose to represent, 1 plus 2, or something like that, or, expression E1 plus E2. We will write that down very simply as, well, we'll need to keep track of the line number. We'll come back to that later. But this is just a plus expression with E1 and E2 in it. So if E1 was something, we will change these out. Let's say this was like the integer 5. Then E2 itself would be its own tuple of another line number and an integer and then 5. So if this was 2 plus 5, E1 would be its line number and another integer and 2. So we're using a nested tuple or nested list representation in order to represent our abstract syntax tree. So we've decided our AST is nested tuples, where we have the line number, the AST node type, and then the AST node child 1, AST node child 2. We have all of those. All right. So that's going to be our plan. All right. What was that input we were trying to parse in again? Let's get out of this example. We were trying to read in test.cl. So we will want to start with a program as a collection of classes. That means we will need to, instead of writing down these rules for integer expressions, we will want some sort of, well, I want to parse a program, all right? And I don't know what goes there. And we'll need to put in our first rule for what a whole cool program is. I don't know what goes here either. How do I find out what goes there? It turns out it's in the cool reference manual. The grammar is listed under cool syntax. Oh, a program is a list of classes, each one of which has a semicolon after it. All right, that seems pretty good. A recurring theme when we're creating our abstract syntax tree is that we will have to represent lists of things. A program is a list of classes. A class has a list of features inside it. All right? And so we'll just make a decision now. When we need to represent a list, we just use a Python list. It's either elegant or cheap, your choice. All right. So we can parse a program from a class list. And whenever you're parsing in a list, if I were to write out this grammar, right, this is like program can either be nothing, or it can be a class followed by another program. But this class would have a semicolon after it. To write that out a little more clearly, I could align it like that. A program is a class list, and a class list is either empty, or it's a class and then a semicolon and then another class list. So these are the grammar rules that we're going to try to encode. So if a program is just a class list, then when I'm building up my abstract syntax tree, conceptually, if I've parsed this class list to the right, I just want to return it on up as the abstract syntax tree I'm constructing. In Python LexYac, and again, this video largely assumes that you've read this documentation and taken a look at what they mean by p bracket 0. This is the return value for the thing on the left of the colon. This is 1, this is 2, this is 3. Here's the P2, here's the P1, here's the P3. We will just want to return the value of the list on the right. So we've said you can parse a program in terms of a class list, but we haven't said how you can parse a class list. Well, there's either the version where it's empty, where it's nothing. So a class list could be just nothing. If that's the case, we return an empty list. Or a class list, we could have one or more entries. Class list could be a class followed by a semicolon. We've written all of our tokens in capital letters, followed by another class list. This is how you represent a list in a grammar. And in this case, what we want to return is essentially the sum of these two lists. We want to put this class in front of this class list. And to make that work out, we'll make the singleton list of P1. Right. So right now we have grammar rules where we can read in a program as a class list. A program is a list of classes, each of which ends with a semicolon. By the way, it's worth noting that the actual cool rules, there's a plus here requiring one or more, and in the rules I've been writing out, you could have 0. Fixing that is left as an exercise to the reader. All right, so now we need to define how you parse a class. And if we take a look back at our grammar, for a class, there are basically two ways to do it. We're always going to want to see the keyword class and then a type, and then sometimes classes inherit and sometimes they don't. Let's do the no inherit version. If this is the case, then a class is just the keyword class, right? And then a type, and then a left brace, and then some features. So the type, we'll have a left brace, and then we'll have a feature list, and then we'll have an R brace. Right? And left brace and R brace are the name of these tokens. And things like type and feature list are rules I haven't yet defined. And this is where we actually start making our parsing rules. Right? What does it mean to parse a class? Well, if we've gotten this far, this is where we start using our AST. We represent it as nested tuples. No, that's not what I wanted to copy. This is totally what I wanted to copy. One of the first things we'll need to do is return the line number. Oh. How do we get the line number? Well, Python LexYac told us a bit about it. So p.lineno of num returns the line number for the symbol num. Now in the description, we tell you quite a bit about line number tracking, but the usual rule is that whenever you have a complicated expression, the line number for an expression is just the first token. It's just a first token. So if we're supposed to be using p.lineno, something like that, for symbol num, we're almost always going to be referring to the first symbol, like the line on which class appears. Remember, this one on the left is 0, this one is 1. And then our AST node type, well, for us, this might be called something like class, right? Or class no inherits. We'll see how that goes in a bit. And then there are 2 bits of information we need to keep track of. What's the class name? That's P2. And what's the class feature list? That's P4. And that's what we'd end up returning. All right. And as you can see, when you're writing out grammar rules for this, it's kind of like, pardon me, you're making promises that you'll have to fulfill later. All of these things in uppercase letters, like class and semi and L brace and R brace, those come from the Lexer. Those are PA2, so those are already done. But for all of these things in lowercase, like type or feature list, we need to define them. Like, how do I parse a type? All right. Well, there's basically only one way to do it. You find the type token. All right. And here, once again, we will need to keep track of what the line number is. If you've read the Programming Assignment 3 printout requirements, for every identifier or for every type, we need to be able to say on what line it occurred. And then we'll actually want to, this type, its lexeme will be the string. We'll want to report that as well. Now we need to define how to parse a feature list. And a recurring trick, you'll have to parse many lists, is that a list is either no entries or it is multiple entries. So it could be that a feature list is nothing, at which point we return the empty list. Or it could be that a feature list has at least one entry. The feature list is a feature. And then, each feature ends with a semicolon. Oh my gosh, Cool's evil semicolon rule actually makes sense. No, it's so hideous. And then there's another feature list after that, which could itself be empty, or there could be more of these. And so what we want to do is take P1 and add it to P3. Remember, P2 would be the semicolon token, which we don't care about. But now we've made another promise to ourselves. We've said, there has to be some way to define a feature. And there are actually quite a few ways to have a feature in Cool. It could either be a method, or it could be an attribute, a field, that might have an initializer. Let's not do initializers for now. Let's just do the attribute no initializer case. Just identifier colon type. Right? So we've got our attribute no init case. So a feature could just be an identifier colon a type. Right. Well, if this is the case, remember our abstract syntax tree maneuver. First, we ask for the line number, right, associated with a particular symbol. And then we give this a name, like attribute no init. Where am I getting this name, by the way? Attribute no init? Oh, conveniently, I read the Programming Assignment 3 description, and it tells you what we want you to call these when you print them out, when you serialize them. And just to save myself time, I'm going to pick exactly the same names so that it's much easier to print out later. So for example, I'll even put this underscore in here. Yeah, maybe that'll be handy. And then if there's no initializer, the two arguments are the identifier and the type. So that's P1 and P3. We're almost done, but we haven't said how to make an identifier. An identifier is going to be a lot like a type. We'll need to gather up the line number and also gather up the string or the lexeme involved. So potentially, at this point, if I haven't forgotten any of these rules, we have enough grammar rules to parse. What was our test file, right? Class main left brace. Here's an identifier, colon type. Here's a semicolon, right brace semicolon. We might even be able to parse that in. So now we need to build the PA3 parser from the above rules. To figure that out, we will go back to their definitions, and we'll want to look for one of these examples of how you actually, here we go. You make your parser by calling something like yak.yak. Let's just look around and see if there are other places we can find that. We'll just find one of their examples. All right. Yeah, your parser is yak.yak. All right. So we'll call our parser is yak.yak. And then after that, we want to actually do the parsing. All right. So our result is what we get by calling parser.parse. And for us, we need to hook up our special lexer. And this is where we go back to miscellaneous Yak notes. And remember it said, oh, to use your own custom lexer, like our PA2 lexer. All right. We instead, and they've used the same name, right? We'll call this abstract syntax tree. We want to call yak.parse, and our lexer is x. Our name isn't that, it's PA2 lexer. Where was PA2 lexer defined? Way up here. PA2 lexer was an instance of this class. And if all of this works, we should be able to print out our abstract syntax tree and see it in tuple format. Now, what are the odds that we've written something that has absolutely no Python errors? Very low. But let's try it out. We want to run main.py, and we're going to pass in our lexer tokens. All right, so one of the first things it tells us, no p error function defined. Oh, that's important. We'll definitely need that later. But it tells us that symbol lbrace is used, but it's not defined as a token or a rule. Oh, yeah, well, up here where we say more here, I totally forgot it. So let's go, add that in. We need lbrace and rbrace. Those are definitely tokens. And now let's rerun it, just in case there were some cascading errors. All right, it says token times plus an integer are defined but not used. They are correct, right? Those were defined but not used. Just to make those messages go away, I'll comment them out for now. So now it's telling us that no p error function is defined and that it's generating LALR tables, but look at this. This is our abstract syntax tree. It's not serialized exactly the right way, but it says, look, on line 1, there's a class with no inheritance that's named main on line 1, and then there's an attribute with no initializer, and then here we have on line 2 there's an x, and on line 2 there's an integer. And let's actually just take a look. Remember, what are we trying to get out of this? Oh, it looks like we never made it. This is the final serialized output we'd like, and if it all fits on the screen, you'll notice this pretty much lines up, right? We've got 1, and then 1 and main, and then the word no inherits. So these 4 things, right? It's just, we need to print them out in just a slightly different order in order to make the grader happy, right? And then we've got this attribute no initializer, which goes to 2 and x, and then 2 and int. Although it looks like our rule for attribute with no initializer, the line number for it doesn't look quite correct. So that's something we may have to come back to in just a bit. We will see how that goes. All right. So we have parsed things incorrectly, and now, rather than printing out the AST, like this prints it as Python, which is not quite what we want. We instead want to output a PA3 CLAST file. All right. Before we get there, though, there was one other warning they kept printing out for us, which was that we don't have a p error method. Let's go back and see if they tell us how to build one. P error, syntax error in input. The p error rule is defined to catch syntax errors. That looks pretty good. User-defined p error function. Aha. Here's one that is, potentially a little bigger. I guess it turns out that you could be at the end of the file, or there could be a token that we have right here. Let's just copy this p error method and see if we can get it to work. Everything associated with our parser has to come above this build the parser line. Right. So we print out syntax error at token, but remember that in there's a particular format we're supposed to write error line number parser message. So this would be error, and then how do we get the line number? All right. Well, once again, we have access to p. We can just look at its line number variable, parser, parse error near, and then we can print out the token. All right. Now, as soon as we see any token, we're supposed to exit. And then, oh, there could be a parse error at the end of the file. Huh. I don't know what the line number for the end of the file is. Maybe I should have tracked that. Maybe I totally won't do that for this demo, but you might be able to figure it out. All right, so we've got our P error little error message, and let's see if it still compiles and works. All right, this seems pretty good, but we haven't actually tested our P error maneuver. So let's go into test.cl, and if I put in a random semicolon here, then it should complain that there's a parse error on line 2. Let's see if it does. Remember, we can't actually feed in these CL files. We have to re-lex it every time. You'll probably want to make some sort of shell script to do your testing. All right. Here we've got error 2, parse error near, semicolon. Now that looks pretty good, except that I'm apparently very bad at calling print in Python. Let's try that again. Error 2, parse error near, semicolon. By contrast, if we were to ask cool on main.py, sorry, not main.py, test.cl, it says error 2, parser near, semicolon, and we are saying error 2, parse error near, semicolon. We're very close to the reference, so we feel pretty happy about that. All right, but when there isn't a parse error, we'll just go back and remove that extra semicolon. And we'll rerun it. We're not quite printing out the output in the format that's expected. And to figure out how to print this out, we would read the CL file format very carefully. To output an abstract syntax tree, a cool abstract syntax tree is a list of classes, output a list of classes. To output a list of anything, you always output the number of elements and then a new line and then each element in turn. To output a class, we output the name and then either no inherits and then the list of features. And to output a list of features, it's a list, so we'd output the number and then a new line. All right, so I think we've got it. One of the first things we want to note is that we have to, if the input is foo.clast, then the output, if the input is clx, then the output is foo clast. So our ast file name is like our first command line argument, but I'm going to remove the last 4 characters and instead add on AST. And then I'm going to have my file out handle, and I'll just open the AST file name for writing. And at some much later point, I will want to close it. And what I will do is define a number of print foo methods that call each other to serialize the AST. For example, to print a class, the first thing I will want to do if you pass in one of these classes, well, what did we get back? Remember that for us, a class is a tuple. So our AST is going to be first the line number, and then class no inherits, and then a class name, right? This was the name, and P4 was the feature list. This name was some sort of identifier or type, so I'm going to need to be able to print out this identifier or type. I guess this time we'll use slightly different tabbing. So the first thing I should do, again, where am I getting this? To output a class, output the class name as an identifier. All right, so there's some sort of print identifier for AST1, 2, 3. AST, sorry, 0, 1, 2. I can totally count. This is me totally not counting. And then, for us, the classes that we're considering are always no inherits. We come back to that later. But I've only shown rules for no inherits. And then we need to print a list of all of the features. We are going to be printing a lot of lists. Lists of features, lists of arguments. So I can't help myself. I'm going to use some higher order functional programming. Oh, it's so exciting. I'm going to make a generic print list method where you give me an AST element and a print element function. You're going to pass in a function to a function. It's going to be just like exam 1, so you should totally pay attention. higher order function. Oh, this is fantastic, right? And the rule for printing out a list is that the first thing you do for any list is to output the number of elements. All right, so that would be the length of this AST, but actually let's convert it to a string first, and then whenever we're using fout.write, we always have to put in every new line we want. And then for every element in that AST list, I just call your print element function on that element. So to print out a class, first we print its name, and then we need to print a list of the features. That's our AST Mark III, and we'll have some sort of print feature function that I haven't quite defined yet. All right. How do we print a feature? Well, the only feature we have so far is this one, right? A feature starts with the line number at position 1, and then the one we have is attribute no init, but maybe later on we'll get an attribute with an initializer. Let's go see how the web page tells us to write that out. Output the name of the feature and then a new line and then any subparts. All right, so the name of the feature is this identifier over here in position 0, 1, 2. So the first thing we will do is print the identifier at AST2. All right. And sorry, the first thing we're supposed to do is write attribute no init and then the identifier and then the type. All right, I can totally do that. Here I've written attribute no init. Here we've printed the identifier, and here we've printed the type. Here's our way of printing out features. All right, once we have a way to print out one class, it turns out that an entire program was just a list of classes. So we'd call our print list function on our abstract syntax tree and use the print class function to print every element. And then if we've actually, rather than printing out this AST as Python, our final maneuver would be to print the entire AST to this file and then close what we have going on. So to print a program, we're going to print a list of classes. To print a class, we're going to print features. Every feature is attribute no initializer, and here we have a way of printing lists. And these sorts of things, all of these print functions, this is how you serialize. Let's see if we've been able to do this with no errors. The odds are low. Now that we're writing to this CLAST file, we'll want to remove it every time we're doing the testing, just to make sure that we're really writing it and not the reference compiler. All right. And it says invalid syntax. No, it's so right. I forgot the comma. Oh, embarrassing. All right, let's try it again. And it says, print identifier is not quite defined. Print identifier. Oh, you know, they're right. Huh. I forgot to define it. All right. What does an identifier or a type look like? Well, this is what we got when we were parsing. It's the line number followed by the string. Well, how are we supposed to print an identifier? To output an identifier, I can't take it, wrap it. All right, love it. Output the source file line number, that's part 0. Oh, this 4, oh my gosh, it's typo-tastic. All right, file output, we'll want to write AST bracket 0, but we'll cast it to a string and then add a new line. Oh my gosh, all these semicolons, you can tell I normally program in some language that has more semicolons. So we've output the source file line number and then a new line, and then the identifier string, and then a new line. Still can't spell. All right, so then we will write out AST1, and then a new line. So this was the source code line number, and then a new line, and then the actual identifier string, and then a new line. That's how we print an identifier. All right, let's see how this goes. Frout, yeah, I'm sure. How many times have I misspelled this? 500 times. Ah, all right. So our test CLAST file 1, 1, main, no inherits, 1 attribute, no init, 2x, 2 init. Huh. I mean, that looks pretty good, but is it right? Well, it turns out that we can run the reference compiler and ask it to parse test CLX, but put the output in a different place, like ref for reference. And now we could take a look at ref.clast and just compare. 1, 1 main, 1, 1 main, no inherits 1, no inherits 1, attribute no init, 2x, 2 int, attribute no init, 2x, 2 int. All right, as lyrical as that is, we probably don't want to do this comparison, manually every time. So we could use something like diff, where these b's mean ignore white space, and we're going to compare our result to the reference result. And if there's no output, we got it exactly right. Oh my gosh, there's no output. We got it exactly right. The mind boggles. Dare we try to submit already? Well, let's try it out for a little bit. So we will need to make some wrw6y zip file, and I'll want to put in all of the Python files, including Lex and Yak that came with PLY, just in case the grading server doesn't have them. And now, live submission demo, assignment and grading, log in, choose file, wrw6y. We're submitting the parser. Oh, just testing. Oh my gosh! Class with 1 field, we're passing. Class with 2 fields, we're passing. Empty class, not class no fields, we're totally passing. 2 classes, oh, an embarrassment of riches. 2 classes with 1 field, we're passing. And we're getting a bunch of negative tests right, but probably not because we deserve it, but because we reject so many programs, right? Because our grammar isn't really that big, right? So now we could do more of these, but you would just, sort of add the rest of the grammar. Let me show you a bit of how that goes. Right now, we only support attributes or fields that have no initializer. Right? The only feature we have is an attribute with no initializer. Let's add support for an attribute with an initializer. Let's just go back to cool syntax. We could also have left arrow expression. So let's add that rule. Let me just show you. This is what we want. We want to be able to parse in some expression initializer like this. And I will just do integers plus and times, but this will also show off precedence and associativity, like the times is supposed to bind more tightly than the plus. So we want to be able to parse this. Right. So now we also have this attribute yes init rule, right, where there's an identifier, a colon, a type, a left arrow, and then an expression. And now this is an attribute with an initializer. Let's just double check and make sure that's how we're supposed to print it out. Yep, attribute with initializer. That seems pretty good. And in addition to the identifier and the type, now there's also this expression. Oh, but this is one of those promises we've made that we haven't filled in yet. We need to explain how you can parse an expression. And this is where you will spend a lot of your time in this assignment, because there are a bunch of different expression rules. Let's see if we can pull up the cool syntax. All of this stuff, right? Assignment, blah, 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 blah. These are all expressions. We're just going to do like these, plus, minus, and maybe integer. Right? So we could parse an expression from plus, and that says that an expression could be an expression plus another expression. And if that's the case, we will once again want to start with a line. This will be a plus node, and its 2 children will be 1 and 3. And we could also parse an expression that's a minus node. Or we could parse an expression that is an integer. And let's take a look at how integers are supposed to be emitted. If it's an integer, you just need the integer constant. You don't also need the line number 5,000 times. So we can just have that. So now we have 3 rules for expression. Now if we try to run this, it's not going to work, but I want to show you some of the error messages so that you'll know how to debug things later. So first we will lex up init.cl, and now we're going to run main.py on init.cllex. All right. Invalid syntax on line 35. Yes, 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 you're right. So there are also other errors that I was hoping to show off. All right, so it tells us, look, all of these symbols, left arrow, plus, minus, and integer, we have to put them back in here. Oh, and we also need this left arrow. We have to list every token we're using so that it knows how to interpret these rules. All right. Minus is not used. Times is defined. Oh, so it's not. Yeah, plus and times. I didn't actually want to do minus. I wanted to do times so that we can show off precedence and associativity in a bit. All right. Oh, look at this. 4 shift reduce conflicts. Now we talked about these in class and there are resources available, but it turns out that they've created this parser.out file in the current directory, which we can read to find these shift reduce conflicts. Now, we know from the class materials that the problem is plus and times, right? We didn't say which one binds more tightly, but sometimes you won't know. So let's go see how we can figure it out from this file. And parser out, this just shows us all of the parse tables and states and blah, blah, blah. All of these various rules like, oh, look, here's rule 11 and rule 12. These are the plus and times kind of maneuvers. And now we'll just search for conflict. And in class, we'll talk a bit about how to read these parsing items. But this dot is where we are now. And the issue is if we've parsed one expression and then the next thing is a plus or the next thing is a times, we don't know what to do. So if you'll notice, just by even if you sort of you haven't internalized all this stuff about parsing yet, it's telling you because the lines are right next to each other, the problem is plus and times. The problem is plus and the problem is times, right? So, okay, great. It has told us that those are the issues. Well, how do we resolve that? Well, actually in our calculator example, I think we saw it, but let's just search for precedence rules via precedence rules. It turns out that there's just a way of specifying precedence, right, that you put up next to your token definitions. And you indicate their relative ordering. So plus is left. We don't have a minus yet, but you could. And we don't have a divide yet, but this tells you which one binds more tightly. Binds more tightly. So now when we rerun it, it should not say shift errors, and it didn't, and that was pretty good. All right, but now when we're printing out a feature, right, we're not actually printing out the right thing. We just assumed this was attribute no init, but we should actually check. If AST1 is equal to attribute no init, then this is the right code. But it could also be that it's equal to attribute init, at which point we print out something different. So here, the world looks like this, but for an actual initialized attribute, let's just go back up to where that was. We have another part of our abstract syntax tree. We have all the same parts as before, but we also have the expression on the right. So let's look up how to print this out. We want to print out an attribute with an initializer, the name, and then the type, and then the expression. All right, so we print the name and the type, and now we need to print the expression. But we don't have a print expression method yet, so now's a good time to add one. All right. And our expressions, let's see if we can find a few of them. All right. Our expressions look a bit like one of these. So the way we print out an expression is going to involve checking to see what this part is, what the node type is. So if it's equal to plus, right? Or indeed, if it's in minus, we can actually do this pretty quickly. If it's in either plus or minus, well, how do we print those out? To output an expression, output the line number of the expression and then a new line. All right, well, the line number is always AST0 and then a new line. All right, so we've done this. And then it says output the name of the expression and then a new line and then any subparts. So here, the name of the expression is AST1. And then we would output any subparts. That's just the left child and the right child. Okay. Else, if it is integer, how do we print out an integer constant? You print out the word integer and then a new line and then the integer constant. All right, so once again, we print that out and then we will just print out the integer constant. And it's often good practice for these unhandled expression to add in a default case so that if you add some stuff later and forget about it, you'll know. And you'll be able to find this sort of failed assertion and come back to it. All right, so let's see if this code still runs. Invalid syntax on line 192. F out right. We've cast the string. We have too many close parentheses. We've run it. All right. Well, let's see what we produced. This looks like the integer 1, 2, 3, the integer 4, 5, 6, the integer 7, 8, and 9. But to really compare, we are going to ask the reference parser to parse init.cl and put the output in ref. And then we're going to diff ref clast with what we produced. And there is a slight difference. This gives us something, sort of interesting to investigate, right? Or a debugging option to try to take a look at. We always love these. Let's see if we can view this in a unified diff format. We notice that in the reference output, let's see if we can find that. No. This integer here, right? One of them says 2 and one of them says 0 right before plus. There are a number of visual tools for viewing different outputs. Vim comes built in with one of them, and this might make it a little easier to see what's happening. All right? One of them is the line number in front of the plus. The other is the line number in front of the minus, and then we appear to have, we've said plus and minus, but they've said plus and times. Well, this part, oh my gosh, what an embarrassing mistake. We named our token the wrong thing. When we parse in a times, we mistakenly print out, we were printing out minus instead. So now if we rerun, jobs, do we have anything running? When we once again do a diff, we see that the only difference is right after int, right before this plus. The reference version says that these things are occurring on line 2, and our version is saying that these things are occurring on line 0. Oh, very interesting. I wonder why that is. Well, where are we getting the particular line number that we're considering? Right? We were calling p.lineno1, but maybe p.lineno only works for tokens, and instead we would need to go into this expression and get its actual line number. Every expression for us in our abstract syntax tree format always starts with the line number as element 0. So one potential way to get this, we'll just comment this out temporarily. If we're not getting the right line number, if it's returning 0, maybe we could get P1 zeroth element. Maybe we could find the zeroth element of this and return it. And then similarly here for times. But let's try this out and see if this causes us to get the right line number for plus. Oh, look, very good. Now we only have one difference. All right. So down here, again, PLY no only works for things written in uppercase letters. So we will need to get P1 bracket 0. And now, there are no differences. We have exactly the right answer, and we have parsed a cool file that has complicated integer expressions. And then what you would do for the rest of the assignment is just go through and add all of these other rules. Times, divided, equals, less than, let bindings, all that fun stuff. All right, so we took a look at testing, we had error reporting, we did the submission. Yes, I think that's it for this particular walkthrough. Talk to all of you later. Bye.